Double-layer surface science. A double-layer DL, also called an electrical double layer, EDL, is a structure that appears on the surface of an object when it is exposed to a fluid. The object might be a solid particle, a gas bubble, a liquid droplet, or a porous body. The DL refers to two parallel layers of charge surrounding the object. The first layer, the surface charge either positive or negative, consists of ions adsorbed onto the object due to chemical interactions. The second layer is composed of ions attracted to the surface charge via the Coulomb force, electrically screening the first layer. This second layer is loosely associated with the object. It is made of free ions that move in the fluid under the influence of electric attraction and thermal motion rather than being firmly anchored. It is thus called the diffuse layer. Interfacial DL are most apparent in systems with a large surface area to volume ratio, such as a colloid or porous bodies with particles or pores respectively on the scale of micrometers to nanometers. However, DL are important to other phenomena, such as the electrochemical behavior of electrodes. DL play a fundamental role in many everyday substances. For instance, homogenized milk exists only because fat droplets are covered with a DL that prevents their coagulation into butter. DL exist in practically all heterogeneous fluid-based systems such as blood, paint, ink, and ceramic and cement slurry. The DL is closely related to electrokinetic phenomena and electrocaustic phenomena. Development of the interfacial double layer. Helmholtz. When an electronic conductor is brought in contact with a solid or liquid ionic conductor electrolyte, a common boundary interface among the two phases appears. Hermann von Helmholtz was the first to realize that charged electrodes immersed in electrolyte solutions repel the co-ions of the charge while attracting counter-ions to their surfaces. Two layers of opposite polarity form at the interface between electrode and electrolyte. In 1853, he showed that an electrical double-layer DL is essentially a molecular dielectric and stores charge electrostatically below the electrolyte's decomposition voltage. The stored charge is linearly dependent on the voltage applied. This early model predicted a constant differential capacitance independent from the charge density depending on the dielectric constant of the electrolyte solvent and the thickness of the double layer. This model, with a good foundation for the description of the interface, does not consider important factors including diffusion/mixing of ions in solution, the possibility of adsorption onto the surface, and the interaction between solvent dipole moments and the electrode. Gowey-Chapman. Louis Georges Gowey in 1910 and David Leonard Chapman in 1913 both observed that capacitance was not a constant and that it depended on the applied potential and the ionic concentration. The Gowey-Chapman model made significant improvements by introducing a diffuse model of the DL. In this model, the charge distribution of ions as a function of distance from the metal surface allows Maxwell-Boltzmann statistics to be applied. Thus, the electric potential decreases exponentially away from the surface of the fluid bulk. Stern. The Gowey-Chapman model fails for highly charged DL. In 1924, Otto Stern suggested combining the Helmholtz model with the Gowey-Chapman model. In Stern's model, some ions adhere to the electrode as suggested by Helmholtz, giving an internal Stern layer, while some form a Gowey-Chapman diffuse layer. The Stern layer accounts for ions' finite size, and consequently an ion's closest approach to the electrode is on the order of the ionic radius. The Stern model has its own limitations, namely that it effectively treats ions as point charges, assumes all significant interactions in the diffuse layer are Coulombic, assumes dielectric permittivity to be constant throughout the double layer, and that fluid viscosity is constant plane. Graham. G.C. Graham modified the Stern model in 1947. He proposed that some ionic or uncharged species can penetrate the Stern layer, although the closest approach to the electrode is normally occupied by solvent molecules. This could occur if ions lose their solation shell as they approach the electrode. He called ions in direct contact with the electrode specifically adsorbed ions. This model proposed the existence of three regions. The inner Helmholtz plane IHV passes through the centers of the specifically adsorbed ions. The outer Helmholtz plane OHV passes through the centers of solvated ions at the distance of their closest approach to the electrode. Finally, the diffuse layer is the region beyond the OHV. Bockris/Divinathan/Moulin BDM. In 1963, J.O.1. Bockris, M.A.V. Divinathan and Klaus Miller proposed the BDM model of the double layer that included the action of the solvent in the interface. They suggested that the attached molecules of the solvent, such as water, would have a fixed alignment to the electrode surface. This first layer of solvent molecules displays a strong orientation to the electric field depending on the charge. This orientation has great influence on the permittivity of the solvent that varies with field strength. The IHV passes through the centers of these molecules. Specifically adsorbed, partially solvated ions appear in this layer. The solvated ions of the electrolyte are outside the IHV. Through the centers of these ions pass the OHV. The diffuse layer is the region beyond the OHV. Tracity/Buzanka, Conway, A. Conway. Between 1975 and 1980, Brian Evans Conway conducted extensive fundamental and development work on ruthenium oxide electrochemical capacitors. In 1991, he described the difference between supercapacitor and battery behavior in electrochemical energy storage. In 1999, he coined the term supercapacitor to explain the increased capacitance by surface redox reactions with Faradaic charge transfer between electrodes and ions. His supercapacitor stored electrical charge partially in the Helmholtz double layer and partially as the result of Faradaic reactions with pseudocapacitance charge transfer of electrons and protons between electrode and E. The working mechanisms of pseudocapacitors are redox reactions, intercalation, and electrosorption. Marcus. The physical and mathematical basics of electron charge transfer absent chemical bonds leading to pseudocapacitance was developed by Rudolf A. Marcus. Marcus theory explains the rates of electron transfer reactions, the rate at which an electron can move from one chemical species to another. It was originally formulated to address outer sphere electron transfer reactions, in which two chemical species change only in their charge. For redox reactions without making or breaking bonds, Marcus theory takes the place of Henry Eyring's transition state theory, which was derived for reactions with structural changes. Marcus received the Nobel Prize in Chemistry in 1992 for this theory. Mathematical description. Electrical double layers. The electrical double layer EDL is the result of the variation of electric potential near a surface and has a significant influence on the behavior of colloids and other surfaces in contact with solutions or solid-state fast ion conductors. The primary difference between a double layer on an electrode and one on an interface is the mechanisms of surface charge formation. With an electrode, it is possible to regulate the surface charge by applying an external electric potential. This application, however, is impossible in colloidal and porous double layers because for colloidal particles, one does not have access to the interior of the particle to apply a potential difference. EDL are analogous to the double layer in plasma. Differential capacitance. EDL have an additional parameter defining their characterization, differential capacitance. Differential capacitance, denoted as C, is described by the equation below. C equals D S D PS backslash display style C equals backslash frac D backslash sigma D backslash psi, where S is the surface charge and PS is the electric surface potential. Electron transfer in electrical double layer. The formation of electrical double-layer EDL has been traditionally assumed to be entirely dominated by ion adsorption and redistribution. With considering the fact that the contact electrification between solid-solid is dominated by electron transfer, it is suggested by Wang that the EDL is formed by a two-step process. In the first step, when the molecules in the solution first approach a virgin surface that has no pre-existing surface charges, it may be possible that the atoms/molecules in the solution directly interact with the atoms on the solid surface to form strong overlap of electron clouds. Electron transfer occurs first to make the neutral atoms on solid surface become charged, i.e., the formation of ions. In the second step, if there are ions existing in the liquid, such as H+ and OH, the loosely distributed negative ions in the solution would be attracted to migrate toward the surface bonded ions due to electrostatic interactions, forming an EDL. Both electron transfer and ion transfer coexist at liquid-solid interface.